Hello students, this is our 8th session of chapter 3 data representation. In this session we are going to study about how to convert from hexadecimal to decimal conversion. Hexadecimal to decimal conversion. So what is the first step? The first step is we have to multiply each digit of the hexadecimal by its positional weights. Multiply each digit of the hexadecimal number by its positional weight. Step 2, add all the products. So what is the first step? The first step is we have to multiply each digit of the hexadecimal number by its positional weights. In the step 2 we have to add all the products. So the first problem is 7b base 16. What we have to do? We have to multiply each digit of the hexadecimal by its positional weights. That is 7 into 16 plus b into 16. So add the powers from right to left, that is 0 and 1. So what is 7 into 16? 7 into 16 is 112 plus b. What is b? In hexadecimal numbers we are going to represent 10 as A, 11 as B, 12 as C, 13 as D, 14 as E and 15 as F. So what is the value of B? The value of B is 11. 11 into 16 power 0 is 1. So 11 into 1 is 11. So add the numbers, which is nothing but 123 base 10. 123 base 10. Next problem, D3 base 16. What is the value of D? The value of D is 13. So 13 into 16 plus 3 into 16. So add the power 0, 1. What is 13 into 16 power 1? Which is nothing but 208 plus 3 into 16 power 0 is 1. So 3 into 1 is 3. So add the numbers 211 base 10. 211 base 10. Third problem is CA base 16. What is the value of C here? The value of C is 12 and the value of A is 10. 12 into 16 plus A into A is nothing but 10. 10 into 16. Add the powers. 12 into 16 is 192 plus 16 power 0 is nothing but 1. So 10 into 1 is 10. 202 base 10. 202 base 10. Next problem, 521 base 16. So multiply by its positional weights. 5 into 16 plus 2 into 16 plus 1 into 16. Add the powers. 0, 1, 2. 5 into 16 square, which is nothing but 256, plus 2 into 16 power 1 is 16. So 2 into 16 plus 1 into 16 power 0 is 16 power 0 is 1. Hence 1 into 1 is 1. So what is 5 into 256? Which is nothing but 1280 plus 2 16s are 32 plus 1. Add all the numbers. The value is 1313 base 10. 1313 base 10. The decimal equivalent of 521 is 1313 base 10. Next problem. Fifth problem. 5AF point D base 16. Yes. 5 into 16 plus A represents 10. So 10 into 16 plus F represents 15 in hexadecimal number system. 15 into 16. So for the integer part, add the powers from right to left. So 0, 1, 2 plus, what is the value of D? D represents 13. So 13 into 16 power minus 1. 16 power minus 1. What is the value of 16 square? 16 into 16, which is nothing but 256. So 5 into 256 plus 10 into 16 power 1 is 16 plus 15 into 16 power 0 is 1 plus 13 into 1 by 16 power 1. So what is 5 into 256, which is nothing but 1280 plus 10 16s are 160 plus 15 ones are 15 plus 13 into 1 by 16, which is nothing but 0.8125. 0.8125. Add all the numbers. 1455.8125 base 10. The decimal equivalent of 5AF point D16 D base 16 is equal to 1455.8125 base 10. So in hexadecimal to decimal conversion, we are going to multiply each digit of the hexadecimal number by its positional weights. In the step 2, we are going to add all the products. So this is how we are going to convert from hexadecimal to decimal conversion. Next type of conversion is hexadecimal to octal conversion. Hexadecimal to octal conversion. So what is the first step? The first step is to write the binary equivalent of each hexadecimal digit. Write the binary equivalent of each hexadecimal digit. Each hexadecimal digit. In the step 2, regroup them into 3 bits from the right side with zeros added if necessary. Regroup them into 3 bits from right side with zeros added if necessary. Next, convert each group into octal equivalent. Convert each group into its octal equivalent. So what are the steps we have to follow? In the first step, we have to write the binary equivalent of each hexadecimal digit. In step 2, regroup them into 3 bits from right side with zeros added if necessary. In the third step, convert each group into its octal equivalent. Convert each group into its octal equivalent. So for this we require table, that is hexadecimal to binary. So for hexadecimal numbers, we are going to represent it with 8421 code. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F. So how to write the hexadecimal numbers in binary form? The shortcut method is, in the first column we have to write 8 zeros and 8 ones. In the second column, 4 zeros, 4 ones. In the third column, 2 zeros, 2 ones. 2 zeros, 2 ones. For last column, 1 0, 1 1. 0 1, 0 1. Yes. In the same table, I am going to represent the octal numbers in binary form. So octal means 8. So that is, it contains numbers from 0 to 7. So for that we are going to represent in binary form, that is in 4 to 1 combination in 3 bits, right? So if I neglect the first column, so this is for 4 to 1 for octal numbers. So if I include the first column also, so this is for the hexadecimal numbers. So let's solve some problems. The first problem is FADE, F-A-D-E base 16. What is the first step? The first step is we have to write the binary equivalent of the hexadecimal digits. So F, A, D, E. So F represents 15 in hexadecimal. So what is the binary equivalent? Double one, double one. Double one, double one. For A represents 10. The binary equivalent of 10 is 10, 10. 10, 10. D represents 13. That is 1101. 1101. E represents 14 in hexadecimal number. The binary equivalent is 1110. 1110. What is the second step? We have to regroup them into 3 bits from right to left. So group it into 3 bits. So here there is a shortage of 2 bits. So I am going to add 2 zeros at MSB. Now write the octal equivalent for these binary numbers. For each group we have to write the octal values. So what is 001? See, for octal numbers we have to neglect this first column. So neglect this first column. What is 001? 001 is nothing but 1. What about 111? 111. 111 represents 7. 101. What is 101? 101 represents 5. Write 5 here. Next, 011. What is 011? 011 represents 3. 011. Again 011 is nothing but 3. 110. What is 110? 110 represents 6 in octal number. 6. Hence, the octal equivalent of FADE is 175336 base 8. Base 8. Second problem, F base 16. What is F? F represents 15 in hexadecimal number. So the binary equivalent of 15 is 1111. 1111. In the second step, what we have to do? We have to group them into 3 bits from right side. Here there is a shortage of 2 bits, hence I am going to add 2 bits at MSB. 2 zeros at MSB. So what is 001 represents in octal number? 001 represents 1. 111 represents 111 represents 7. Hence the octal equivalent of F base 16 is equal to 17 base 8. 17 base 8. Next problem, 912 base 16. What is the value of 9? The value of 9 is 1001 in hexadecimal. 1001. What about 10001? 0001. For 2, 0010. 0010. First, what we have to do? We have to write the binary equivalent of hexadecimal numbers, that is in the form of 8421 code. Next, in the next step, we have to regroup them into group of 3 bits. So, group from right side. What is 100? 100 represents 4 in octal number system. 4. What is 100? Again, it is 4. What is 010? 010 represents 2. What is 010? Again, it is 2. Hence, the octal equivalent of 912 base 16 is equal to 4422 base 8. Next problem. C1 base 16. So what does C represents in hexadecimal number? C represents 12. So what is the binary equivalent of 12? 1100. 1100. What about 1? 0001. 0001. Now regroup them into group of 3 bits from right side. So here there is a shortage of 1 bit. So I am adding 1 zeros at MSB. So what is the value of 011? 011 is nothing but 3 in octal. 000 represents 0. What is 001 represents? 001 represents 1. Hence, the octal equivalent of C1 base 16 is equal to 301 base 8. 301 base 8. So, in hexadecimal to octal conversion, what we have to do? First, we have to write the binary equivalent for each hexadecimal digits. In the next step, we have to regroup them into group of 3 bits from right side to the left side. If there is a necessary, we can add zeros at MSB. Then we have to convert each group into its octal numbers. This is how we are converting from hexadecimal to octal conversion. Thank you.